students, today in continuation to my videos, I will discuss some important things regarding the Gauss theorem, charge distribution and its applications. Now first thing is continuous charge distribution. Have you heard about that how the charge is distributed? Earlier the charge was discrete one and we are talking about the charge distribution, continuous charge distribution. If the charge magnitude is high and it is distributed over any body, then what will be the way of the charge distribution? Now, do you know that we ignore quantization when the magnitude is high? So, charge distribution is done in three ways. One is simple, it is the linear charge distribution. Another is the surface charge distribution. And the last one is volume charge distribution. So three types of charge distribution are there when the charge is continuous. So linear, that means with respect to length. Okay. Then surface area. Then volume. Okay, the linear charge distribution. We'll talk about the linear charge distribution. Simple. When the charge is distributed with respect to length. Say there is a wire for any linear body. So charge is distributed like this. Charge is distributed on the surface of the body. So if it is length L, then there is a density known as linear charge density. So linear charge density. Okay. So linear charge density is denoted by lambda. So it is charge per unit length. And for small length, you know that it can be written as lambda equal to dq by dl. So this is linear charge density. If you want to find out the whole charge, you can even write q lambda dl integral. So this is lambda q by l. SI unit is coulomb per meter. So charge is distributed with respect to length. Got it? And then surface charge distribution. So for a surface charge distribution, it is simple. You take any charge surface like this one you have taken, and this is having a charge on its surface, and say S is the surface area, okay, and Q is the charge on it. So again there will be another thing, sigma. Sigma is what? Charge per unit area. So sigma is denoted for what? Surface charge density. That means we are going to talk about the surface area. And then if you want to find out for a small one, say it has a ds area. ds is a small area. So it will be having which charge? dq charge. Continuous distribution. So even sigma can be written as dq by ds. If you want to find out q, you can find out sigma ds. So this is for surface charge distribution. And now for the another one, for this SI unit will be coulomb per meter square. Okay. And then after surface charge distribution, we have volume charge. So we know that volume charge distribution means if you have any solid body, okay, like we say that this is a solid body and it has a charge on it, and we know that its volume is V. So the charge is distributed with respect to volume. So here we have rho Q by V. Q is the charge distributed on it. So this is which density? It is what? Volume charge density. Volume charge density. Okay, so this is SI unit is what? Coulomb per meter cube. And for a small, we have a ds, and we have a ds surface area and dq charge. So certainly rho can also be written as dq by dv. So if you want to find out, it will be again integration of this. So this is what we call volume charge distribution. SI unit is coulomb per meter cube, already written here. So in this way we have three type of charge distribution: linear for the length, linear things, and surface area for that surface charge density, and for any solid body we have volume charge density. So these are the three things which we have discussed for the continuous charge distribution. Now, very important theorem we are going to talk about is the Gauss theorem. But before going to the Gauss theorem, we have a very small concept, Gaussian surface. Now, what does it mean by Gaussian surface? Is very simple, that it's a hypothetical surface around any charged body. Okay, we can create an hypothetical surface. Say there is a charge q here, so we can create a surface around it like this. Now this is a type of a Gaussian surface. Now this is a point charge. Some of you will say, why this is a spherical? Because q is a point charge. We see the spherical symmetry, the point charge. So this is a Gaussian surface or point charge. That means charge will be enclosed inside it. Similarly, if I talk about the wire, a wire will be like this, and when the wire is like this, a wire will have a cylindrical symmetry. So for this, we can have a cylindrical Gaussian surface. So Gaussian surface is a hypothetical surface around any charged body where you can calculate electric field, electric potential due to a charge. So before going to Gauss theorem, we should know about the Gaussian surface. Now the most important theorem and the law is the Gauss theorem, and that is, we are going to talk about Gauss law or Gauss theorem. Now Gauss's theorem is what already we have done. Electric flux, you remember, E dot S, EA cos theta, EDS for d phi, EDS cos theta. So what is the statement? You know that it states that total flux through a closed surface is 1 upon epsilon naught times the net charge enclosed by the closed surface. So I can write it here. The total flux, that means electric flux through a closed surface, that means it is acting on closed surface, okay, is 1 upon epsilon naught times the net charge enclosed by the closed surface. So this is Gauss theorem, and some of you may understand why I gave the concept of Gaussian surface. So this is Gauss theorem, and if I ask you what is the mathematical form, so phi is what? E dot ds, integration of E dot ds, and it is even written as q by epsilon naught. So this is the way we write the Gauss theorem. Now what is this? Do you know? This stands for closed integral. Some of you may be knowing about the integration. When you write this circular, that means always it acts on closed surfaces. That is why we talk about the what? Gaussian surface. So how we are going to derive Gauss law? That is also very important. How phi will be what? Q by epsilon naught. So we'll talk about that also. Now the proof. We are talking about the proof of this Gauss theorem. Very simple. How we are going to prove it is that there is a charge, say there is a point charge Q, and you know that, and if there is a point charge, certainly there will be a Gaussian surface like a solid sphere, like a sphere here, and this is a point charge. And what is the radius? Say R is the radius, and this is the ds surface. And all of you know that the point charge, the electric field will be outward, and you know that area vector perpendicular to it, it will be also outward. What is the angle between E and ds is here 0 degree. So you can take it anywhere. Anyway, total surface is S, but for you have taken ds. So very simple, we are going to start the Gauss theorem, and we will say that d phi is the electric flux associated with ds surface. Okay, ds surface area. So d phi will be written as E dot ds. I think most of you know E dot ds. Phi is E dot s, so d phi is E dot ds. So net electric flux. Okay, so net electric flux will be phi integration of E dot ds, and it's a closed integral. Then finally we know that it will be E ds cos 0. You know that cos 0. So phi will be what? E ds cos 0 is 1, and E will be out, integration of ds. And how many of you know what is the electric field due to point charge? I think all of you know electric field due to point charge is what? You know that it is kq by r square. So it is kq by r square integration of ds, and finally kq by r square. What is ds? It will be surface area, and kq by r square 1 upon 4 pi epsilon naught k q by r square. What is surface area of total? 4 pi r square. So in 4 pi cancels, r square cancel. Finally phi is what? Simply q by epsilon naught. So this is Gauss theorem. This is a very important theorem. Phi is independent. What? Independent of the shape and size. See here, phi is simply q by epsilon naught. So this means that the charge enclosed inside the surface, that is the flux, q by epsilon naught. And if another thing is here, I think all of you know, if any other medium, always we talk about here, remember, any other medium dielectric, any other medium is represented by epsilon, then what will be phi q by epsilon. And how many of you know epsilon is also not written as epsilon naught into epsilon r, and epsilon is written as epsilon naught into k. So phi m will be what? Epsilon naught into k. So can we write phi m is equal to phi air by k? Yes. So this is another way we are going to write electric flux in a medium. So this is Gauss theorem in electrostatics. Now we have some applications based on Gauss theorem. So we'll talk about the applications of based on Gauss theorem, and one of the application is based on for the line charge. So first application is electric field intensity due to infinitely long charged wire or thin line charge. It is written like that also, infinitely thin line charge. Sometimes it will like this, thin line charge. So we will talk about that also. Say this is a line charge, and you know that line charge distribution already we know about this. And this is the Gaussian surface. You remember the symmetry? It's a thin. Now, if I ask you what will be the, say, this is what a surface area for this one, it is say ds. Okay, it is also here ds. Area vector will be what? Outward. Area vector will be outward. Where is the electric field you see here? Above this one, because the charge will take the electric field in upward or downward. So electric field is in this direction. And what is the angle in between them? Is 90 here. It's 90. So I think flux will be 0 here. If I ask you what is the flux from here, this first one, it will be what? EDS cos 90. It will be 0. And from here also it will be 0. See here. So we have only the curved surface area. This one we say consider it as ds and take the area vector upward. Area vector is always outward, and again electric field is also outward here. You see, or you can take it downward. So here theta is what? 0 degree. So this is a line charge. If I ask you, a line charge has, you remember lambda has q by l. We have discussed lambda tha linear charge what? Density. Remember? So flux through cross-sectional area of cylinder is 0. Got it or not? Is 0. If you see this one is 0, this is only the curved surface. So what we see that, consider that d phi is the electric flux, okay, due to curved surface area ds. Only curved surface, so d phi will be what? E dot ds. Again the same thing. Phi will be was integration of e ds cos 0. Okay, so phi is what? E ds. Phi will be what? E integration of ds. Phi is E and integration of ds. And do you know what is E? What is ds? It is S, and S is the curved surface, 2 pi RL, curved surface area. It is curved surface area. Okay, so now by Gauss theorem, we apply Gauss theorem now. By Gauss theorem, what is phi? Phi is Q by what? Epsilon naught. So finally, Q by epsilon naught will be E2 pi RL. And you know what is Q? It is lambda L. So it will be like this, 2 pi RL. And L cancel out. Finally, E is lambda upon 2 pi R epsilon naught. So this is first application of Gauss theorem. E is lambda upon 2 pi R epsilon naught. Got it? E is inversely proportional to R for line charge. Remember, this may be a question. You know that for a point charge, it is R square. For a dipole, it is R cube. For a line charge, it is R. Such type of things, you know, they can ask. So here, this is for line charge, and we have calculated how for a line charge it works. Again repeating, this is the line charge. You see that the cross-sectional area, the flux is 0. Only the flux comes from the what? Curved surface. Then what you did the same thing here, T phi EDS, and then you calculated it. You put it and you get this one. This is a very important thing. And there can be a graph between E and R. And what is the graph? If E is lambda upon 2 pi R epsilon naught, we can draw the graph between E and R. This E and R graph is like this. So E is inversely proportional to R. Remember, where E and lambda is in coulomb per meter, R is in meter, so and E is in Newton per coulomb. So this is how the Gauss theorem first application is given for Gauss theorem. And there can be a question that find the electric field intensity due to a line charge at say 4 centimeter for a linear charge density. Given linear charge density, a linear charge density is say lambda and it is 4 microcoulomb, okay, per meter. Now can you find out it? Yes. What is the solution? The solution for this is, we know that E is what? Lambda upon 2 pi R epsilon naught. Okay. What you can do is that you can make it 2 lambda 4 pi epsilon naught R. Got it or not? 2 we multiply. So it becomes, what is 2? Okay, lambda is given 4 microcoulomb 10 to the power minus 6. And what is 1 upon 4 pi epsilon naught? We know that it is 9 into 10 to the power 9. And what is R? Is 4 centimeter. Got it or not? So it will cancel out and it will be 18 into, what if you take it 10 to the power 11 minus 6, 10 to the power what? 9 into 11 minus 6, 5. Again repeating lambda upon 2 pi. What we did? 2 lambda 4 pi. Why 2? Because we know 1 upon 4 pi epsilon is 9 into 10 to the power 9, 2, and then 4 into 10 to the power 6, and we calculated it, 2 9 18, and then this is Newton per coulomb. So how we apply this can be a 2-mark question in the board exam. So thank you and continuously watch the videos.